Great job, everyone. We did it. We have gone through many chapters and many lessons about fundamental TLS, transport layer security, and have reached the last chapter, which concludes this course with a recap and summary of all the things we have covered. As a last recap, TLS, as a cryptographic protocol, has the primary objective to construct a secure channel from an insecure channel between communicating peers that have never met before. A secure channel is understood to be a channel that provides both confidentiality as well as authenticity to the data exchanged, and an insecure channel is then a channel that is neither confidential nor authentic, and a good example of such an insecure channel would be the channel from the laptop of Alice through the internet to a web server. Without any protective measures, the data exchanged between Alice and the web server through the internet can easily be eavesdropped on or tampered with. What makes TLS as a protocol truly fascinating is that TLS allows to construct such a secure channel between communicating peers, even if the communicating peers involved have never met before. In order to achieve its primary objective, a TLS connection goes through essentially three sub-protocols. The connection starts with a handshake protocol initiated by the client, then proceeds into a protocol for the secure exchange of the encapsulated application data, and when all application data was securely transmitted, the TLS connection proceeds into a protocol to close the connection. Of course, errors such as failing to agree on security parameters or failing to verify a certificate can occur at any time in each of the three subprotocols. As of TLS 1.3, all errors are considered fatal, and upon detection of an error, the detecting party sends an error message to its peer, with subsequently both parties closing the connection. From a cryptographic point of view, the by far most interesting TLS sub-protocol is the initial handshake protocol. This handshake protocol is responsible for constructing the confidential and authentic channel between the client and the server. For this, the handshake protocol authenticates the peers involved in the connection and provides the means for the peers to agree on a master secret. Once a successful handshake finishes, the peers involved in the connection are authenticated and have agreed on a shared master secret. The application data exchanged later on between the peers is then symmetrically encrypted and authenticated with keys derived from the master secret. Clearly, TLS is a complex application of various cryptographic concepts, and interestingly, multiple combinations of cryptographic mechanisms and primitives can be used to achieve the overall objective of constructing a secure channel between a client and a server. The specification of which combination of cryptographic primitives and mechanisms to use is given by what TLS calls cipher suites, and it's such a cipher suite that a client and a server will have to agree on essentially first thing within the handshake. A TLS 1.2 cipher suite explicitly specifies each of the 5 cryptographic processes taking place within a TLS connection in order to have the confidential and authentic channel constructed between the client and the server. Going from left to right across the example TLS 1.2 cipher suite reading TLS ECDHE RSA with AES 256 CVC SHA-256, we can see that the first part following the generic prefix TLS reads ECDHE. ECDHE is an ephemeral elliptic curve Diffie-Hellman key exchange, and such a key exchange serves the purpose of the client and the server agreeing on a master secret. The next part in the cipher suite to the right of ECDHE reads RSA, and this part of the cipher suite specifies that the peers involved in the TLS connection making use of this cipher suite are authenticated by using RSA-based digital signatures. If we go to the next non-generic part in the cipher suite to the right of RSA, we get to a part that reads AES 256 CBC. This part specifies that confidentiality is provided to the application data exchanged after the handshake protocol by symmetrically encrypting the application data with the AES block cipher behind the CBC block cipher mode of operation and using 256-bit symmetric AES keys. The last part of this cipher suite, its tail, so to speak, reads SHA-256, which stands for the SHA-2 cryptographic hash function with 256-bit hash values. Within TLS 1.2, this cryptographic hash function is then used in two places. The first place SHA-2 with 256-bit hash values is used is as part of the HMAC message authentication code that's used to provide authenticity to the application data exchanged later between the client and the server. The second place this cryptographic hash function is used within TLS is as part of the pseudorandom function PRF, which is used by TLS 1.2 to derive encryption keys and keys for HMAC from the initial master secret agreed on by the client and the server. Also, TLS 1.3 cipher suites serve the purpose of fully specifying the 5 cryptographic processes taking place within a TLS connection to construct a confidential and authentic channel between the client and the server. However, within TLS 1.3 cipher suites, only 3 of these 5 cryptographic processes are explicitly specified, and the authentication of the peers and the agreement on a master secret are implicitly specified by TLS 1.3 or otherwise derived. Within TLS 1.3, the authentication of the peers still takes place via asymmetric public-private key pairs or a pre-shared key, where TLS 1.2 cipher suites explicitly specified the type of the public-private key pair. TLS 1.3, however, derives this type either from the corresponding X509 certificate received from the peer, or derives this type from information attached to the raw public key. Also, within TLS 1.3, the peers always agree on a master secret by either using the ephemeral Diffie-Hellman key exchange DHE or ECDHE or a pre-shared key. With this very limited choice, there is no need to have it explicitly specified within a cipher suite, and a client will just optimistically send a selection of supported key exchange methods together with corresponding ECDHE half keys to the server. If the server supports one of the key exchange methods sent by the client, the handshake proceeds. Otherwise, the client restarts the connection with a different set of key exchange methods. Last that we need to know to explain TLS 1.3 cipher suites is that within TLS 1.3, only authenticated encryption with associated data ciphers are used. With this understanding of TLS 1.3, let's now have a look at the first part of this TLS 1.3 cipher suite reading AES 256 GCM. This part specifies the authenticated encryption with associated data cipher, which in this case is the AES block cipher behind the GCM block cipher mode of operation using 256-bit AES keys. GCM as an instance of authenticated encryption with associated data now provides both confidentiality and authenticity to the application data, and as such, we are only left to have the key derivation specified by the cipher suite. The key derivation is then specified by the last part of the cipher suite, and in this case reads SHA-384, indicating the SHA-2 cryptographic hash function with 384-bit hash values. This hash function is then used for the derivation of the keys for the AEID cipher AES 256 GCM. This derivation starts with the agreed on master secret and takes place via the HMAC-based key derivation function HKDF, which is a construction that is built on top of HMAC and as such requires to be provided with a hash function. With the last slide of this recap on TLS, transport layer security, and the last slide of this entire course, I would like to provide a baseline set of security recommendations on which TLS cipher suite to use. Now, these recommendations come without any warranty whatsoever, and the final choice of a cipher suite not just depends on the security implications of using it, but the final choice of a cipher suite also depends on the availability of a cipher suite within an implementation or a library, and the final choice of a cipher suite also depends on interoperability requirements and constraints of a system with its context. Before we get started with the recommendations on TLS Cipher Suite, it's good to be aware that most of the 200 plus TLS 1.2 cipher suites are by now considered insecure. For TLS 1.3, this is the complete opposite, as for TLS 1.3, all of its 5 cipher suites are nowadays still considered secure. Now, a first guiding principle to sort out insecure TLS cipher suites from secure cipher suites concerns the key exchanges. Key exchanges should preferably provide forward secrecy. Forward secrecy is provided by the ephemeral Diffie-Hellman key exchange DHE or the ephemeral elliptic curve Diffie-Hellman key exchange ECDHE. This then rules out cipher suites not providing forward secrecy, which is the case for cipher suites that conduct key exchanges based on RSA encryption or the static Diffie-Hellman exchange DH or ECDH. The use of a pre-shared key is not explicitly ruled out, however, but in case pre-shared keys are used, then pre-shared keys should be used in conjunction with an ephemeral Diffie-Hellman key exchange to nevertheless achieve forward secrecy on the application data exchanged. Moving now into the authentication of the peers involved in a TLS connection, then generally speaking, the authentication should take place via RSA-based digital signatures or ECDSA. The choice between RSA and ECDSA is then limited by the type of X509 certificates available, as X509 certificates either contain a public RSA key or a public elliptic curve key. The authentication of the peers involved in the TLS connection can also take place via a proof of knowledge of a pre-shared key. If a pre-shared key is used, then it's important to ensure that the pre-shared key contains enough entropy of at least 128 bits, and that the pre-shared key was distributed over an otherwise authenticated channel. As no X509 certificates are then involved, a separate mechanism then needs to exist that can revoke a pre-shared key in case the pre-shared key would be assumed to be compromised. Going into the protection of the application data, the Suite 32 attack on TLS made clear that the 64-bit block cipher TripleDES is insecure, and the Lucky 13 attack made clear that the CBC block cipher mode of operation is insecure as well. Additionally, the Stream Cipher RC4 was officially deprecated for use within TLS in the year 2015. For the protection of application data, this then leaves us with cipher suites using authenticated encryption with associated data AEID ciphers such as AES behind the GCM or CCM block cipher mode of operation or JAT20 Poly 1305. Going into the authentication of application data and the cryptographic key derivation with the pseudorandom function PRF and HKDF, where cryptographic hash functions are required, we need to remember that MD5 and SHA-1 are by now considered insecure hash functions. As such, cipher suites using MD5 or SHA-1 should not be used anymore, but cipher suites using SHA-2 with either 256-bit hash values or 384-bit hash values should be used. Last, but now very importantly, all the recommendations just given are recommendations given considering classic computer power. The computational power of quantum computers, however, poses a significant threat to especially the key exchanges ECTHE and the RSA or ECDSA-based digital signatures. As such, and especially looking at key exchanges and digital signatures, for all the algorithms ECTHE, RSA, and ECDSA, we need to be aware of the threat posed by quantum computers and need to be aware that especially these algorithms may need to be replaced at one point by appropriate post-quantum cryptography algorithms resistant to the computational power of quantum computers. I think this was all I had to say about the subject of TLS for this course. I hope that with this course you could develop an intuitive understanding of TLS as a cryptographic protocol that aims to construct a secure channel across an insecure channel such as the internet between two parties that have never met before. Of course, I also hope that you just generally enjoyed this course, that I managed to convey some of my fascination for the subject to you, and that we will get to see each other in another course again. All the best, and see you another day.